13.1b continued is using square roots, but we're actually going to break them down by hand and give a radical answer instead of a 13.606 answer. And how we do that is we have to use this product rule. So real quickly, I want to show you, basically prove the rule works and then write it in generic form. So let's look at the left-hand side first. Order of operations, we would do the roots first because that's a grouping method, and we would multiply last. So what's the square root of 4, guys? 2. And what's the square root of 5? 25. Or 25, yeah. You knew what I am telling you your answer. What's the square root of 25? 5. And so what's 2 times 5? 10. So the question is, does that equal the square root of 100? Yes. And it does, okay? So these are just showing you that if you have one square root times another, you can actually do the multiplication underneath and then take the square root of that. So you'll see on the right-hand side the same thing is true. The square root of 9 is what? 3. The square root of 36? 6. So the left-hand side ends up being 18. But if you throw 324 in your calculator, what do you get for the square root of 324? 18. So we do know that this rule is true. So what typically happens in math is once a rule is discovered, they like to put it in a generic form so it can work for any number. And that's the whole idea of variables. So here, let's just write this generically. If we have a product of our roots, we can actually write it as one giant root with the product underneath. Okay? And honestly, when it comes to doing today's lesson, I don't really even do this a whole lot. I just want to show you that we can kind of separate things and it can work. So this is just showing you two different methods. I personally prefer method 2, and I'll explain why, but I want you to see that both work and get you the right answer. So notice on both method 1 and method 2, we're taking the square root of 45. So what they did is they said, okay, what's the largest square that goes into 45? They said 9. So they wrote it as the square root of 9 and the square root of 5. Do you guys agree that 9 times 5 is 45? Is that okay? And then they just broke it down. They said, I know what the square root of 9 is. It's 3. 5 can't be broken down, so 3 root 5 is actually a reduced radical form of root 45. Over here, I'll tell you why I prefer this. I'm going to just star this method 2 over here. The reason why I prefer this method is what it does is it breaks the entire number down into primes, and once you see that perfect pair or that perfect triplet, that's technically a square, right? What's the square root of 45? Well, 3 times 3 is 9, 9 times 5 is 45, correct? But whenever you see a pair, you have found a perfect square, right? What's the square root of 9? 3. So look who comes out. The 3 and who stays in. And at first it looks more confusing, but the reason why I like it is, for example, let's skip to examples 1 and 2. Does anybody know offhand real quickly the largest square that's into 72?
36.
Right. He's good, right? But how long might it take us to sit here and think, okay, what goes into 72 that's big and it's a square and so forth, right? So method 1 is technically forcing you to do that, okay? So in method 1, they want us to write 72 as the square root of 36 times the square root of 2. Is that okay? Because he realized that 36 was the largest square that was in 72. What's 72 divided by 36? 2. So that's what we know. So when we multiply those two, we get 72. But how does that help us? What's the square root of 36? 6. And so who can come out here? 6, the square root of 2 is not a perfect square, so he stays the square root of 2. Okay? Again, not horrible, but it forces you to know those perfect squares. 49, 81, whatever it may be. The second method is to break 72 down into primes. So I'm going old school. I'm going really elementary here. What we're going to do is we're going to do a factor tree over here with 72. What are any two numbers that multiply to be 72? 8 and 9. What are any two numbers that multiply to be 8? 4 and 2. What are any two numbers that multiply to be 4? 2 and 2. Okay. Can we break the 2's down any further? No. So when we get to the end of that branch, that's your prime. So 8 was broken down to 3 2's. Let's go back up to 9. Can 9 be broken down further? 3 and 3. So the reason why we do this is because we can now rewrite 72. It seems tedious at first, but once you get the hang of it, you don't have to do all this work. I'll kind of show you the shortcut. what we can do is we can write 72 as 3 2s and 2 3s. Do you guys agree that if we multiply those 5 numbers, we would get 72? Why does this help us? Because anytime you see a pair, you have a perfect square, okay? So what is this pairing right here? What is 2 times 2? 4. But what's the square root of 4? 2. So whenever you see a pair, that number comes out singularly. They like hook arms and come out as 1, because you technically have 4, but what's the square root of 4? 2. So 2 will come out, okay? What else do you see a pair of? 3s, right? So really this pair of 3s is 9, but what's the square root of 9? 3. So who can come out? The 3. And as they come out, we're going to multiply them. Who's left on the inside of that radical? The 2. So he'll just stay under that radical. So what we have is exactly what we found in example 1. What's 2 times 3? 6 root 2. Okay? And like I said, at first, this seems kind of tedious, but if Braden didn't shout out 36, it might have taken us a while to figure out the biggest square that was into 72. So I like this because it's the no-fail method. You don't have to think of perfect squares, you just have to think of factors. And once you find that pairing, they can come out, all right? So, for example, 12. That's not too hard to think of the perfect square, but I'm going to force you to learn my method. You don't have to, but what are any 2 numbers that multiply to be 12? 6 and 2. And then how does 6 split up?
3 and 2.
3 and 2. And then can either any of those break down any further, guys? No. Okay? So we're going to rewrite this as 3 times 2 times 2. Is that all right? And then once you rewrite it, it's called the product of primes, meaning they're all the primes are multiplied. You just go and circle your little pairs that can come out and play, okay? So who can come out and play? 2, right? And it's technically 4, but it's under the square root. So what's the square root of 4? 2. So he'll come out, and who stays on the inside? 3. If we did it method 1, which method 1's not horrible with this because it is smaller, what's the largest square that goes into 12? 4, right? So 4 times 3, so that's where that 3 comes from. But what's the square root of 4? 2. All right, 24, I'm going to do my method still. What are any 2 numbers that multiply to be 24? 4 and 6. 4 splits up perfectly. 2 and 2. How does 6 split up? 2 and 3. Okay? And I like how Braden said it because he noticed again that large square that was in there, that 4. So under the square root, we have 2 times 2 times 2 times 3. Who can come out and play? The 2s. And then who has to stay on the inside? The 2 and the 3, but notice they're multiplied. So really what's on the inside? 6. Do you guys see that no matter whether they come out, they multiply, or whether they stay in, they're going to multiply? So this is 2 root 6. 80, is that one, Braden, that you knew right off the bat? That's 16. How do you know these? Do you just kind of go through them in your head real quick and just see if 80 is like divisible by it?
I mean,
or do you have a good number sense?
I just like memorize.
So you have the perfect squares memorized, like 9, 16, and all that, right? So 80, guys, it breaks down. What are any 2 numbers that multiply to be 80?
10.
And that's what I'll always do. Whenever I see that 0 on the back end of a number, I know 10 goes into it. So we have 10 and 8. How does 10 split up? 5 and 2, and then we already know 8 is kind of this little branch over here, right? It's going to be 4 and 2, and then the 4 splits up to 2 and 2. So when we're all said and done, we have a 5, and how many, is it 4 2s? 4, because we're going to have all those, right? And you can always double check by multiplying it and seeing if you get back to that 80, right? If you don't get to 80, you know you just missed one of those factors. All right, who can come out to play? Both chunks of 2, right? These 2 2s will come out as 1, and these 2 2s will come out as 1. So we'll have 2 for this one, a 2 for that one, and the 5 stays in. But who's that going to end up making on the outside? The 4. And that's what Braden saw. Braden saw that 16 went into 80. But what's the square root of 16? 4. So that's why the 4 came out and the 5 stayed in. 75 is the same way. Anytime I think of 75, I think of quarters, right? How many quarters do you have if you have 75 cents? 3, right? So 75 is 3 times 25, but why does that help us? What happens to 25? 5 and 5. So we have 3 times 5 times 5. And notice when I put these in, it doesn't really matter how you put them in, but I always try to put the pairs together if possible, so you see them. Whether they're in the front or the back, it doesn't matter. So what do we end up having? 5 root 3. What I want to show you real quickly is that you have to do these by hand. So whether you use method 1 or method 2, I will not force you. I typically lean towards method 2 because you'll always catch all your perfect squares. For example, here, maybe you caught 4. You're like, 4 goes into 20, and then you said 2 square root of 20. But you're not completely simplified because 20 has what in it? Another 4. So method 1 is kind of hard unless you do have them memorized where 16, 25, and all that stuff goes into them. So method 2 is kind of like the no-fail method, like you can always catch it. So what did I want to show you real quick before we worked on the worksheet is how you cannot do it in your calculator. For example, let's do the square root of 24. You do the square root of 24, and what do you guys get? Right? It's not that radical form. So pay attention to what my math lab asked for, because sometimes they say, what's the square root of 24 rounded to 3 decimals? Well, if they say round to 3 decimals, they want you to put it in your calculator and round to 3 decimals. But if they say in reduced radical form, that means, hey, you better have a radical still hanging out. But what's kind of a nice catch, it's not a catch-all, but it is nice to know that you at least have a reduced form, is type 2 root 6 in your calculator. And what do you get? The exact same number. So you know you've reduced it properly. The question is, have you reduced it far enough? So if you didn't catch the biggest square, guys, you would still get an answer that matched.